A very good morning and good afternoon to everyone. Thank you for joining us today on this webinar, which is hosted by IBM in partnership with Continental. The topic for the webinar is Managing Complexity with Model-Based Systems Engineering, a Continental and IBM example. So before I hand it over to our speakers, for all the participants today, please feel free to post your questions in the Q&A chat section on the right side of your WebEx application. Your questions will be addressed by our speakers in the last 10 minutes of the sessions. So please feel free to post questions and ask your questions in the Q&A section. With that, let me hand it over to our speakers. Gentlemen, take it away.
Thank you very much, Preeti. So welcome everybody. My name is Marco Forlingeri. I am responsible for engineering in IBM, so engineering ASEAN, Southeast Asia. And my main focus in the last 10 years have been model-based system engineering. And now we also have Enrico Seidel from Continental. Please, Enrico.
Hello, thank you for the opportunity to be able to join this webinar today. My name is Enrico Seidel, age 50. My role is to work in Continental as an expert for the system engineering, especially model-based system engineering. I'm originally from Germany, but based in Continental in Singapore. I work roughly, almost 7 years in the system engineering area for Continental.
Thank you very much, Enrico. So let's get it started. And so let's have a quick look at the agenda together. First, my part will be focused on introducing to you the topic of MBSE and how it can be used and applied to manage complexity and boost innovation. And then I will hand it over to Enrico. Enrico will introduce the Continental case, basically showing what it's doing and what has been doing in the last year, how Continental is applying model-based system engineering for innovation to manage complexity on a specific case. And then we will deep dive into this specific case with the live demo done by Enrico. And at the end, as Preeti already mentioned, we will have 10 minutes for a Q&A session. So let's start with the first topic. And well, probably most of you belongs to engineering companies that either develop software or systems. And today we focus on automotive. And the automotive industry has been seeing in the last 20 years a very big increase of complexity. So the increase of complexity is mainly due to a high amount of functionality, high amount of interdependencies, that a high amount of regulation as well, that are transforming the way cars are produced and of course later, once in operation, driven. So which are the key drivers of this complexity? According to, not myself, but to INCOSE, the International Council of System Engineering, in the System Engineering Vision for 2035, two main drivers are mentioned for this increase in complexity. First is the technology-driven complexity. What does it mean? It means that before cars, let's have a look at the car, mainly we had a type of development that was more mechanical and electrical intensive. Then we have the era of electronic. We went into the software era, so where the software started to be more and more important. But now we are already overcoming this era and we are entering into the network intensive and algorithm intensive. What does it mean? That cars are connected, cars needs to adapt their behavior. Imagine the topic of autonomous driving, for example. So there is a change of a technology that is driving this type of complexity. And then we have a second driver. The second driver is the scope. Before, each team in engineering organization, automotive organization, for example, were focused on developing the ECU, the specific function, the specific component, the box. And then we are going more and more into integration of the different box, integration of the ecosystem of suppliers, up to now a system of system topics. So it's not the car anymore, but it's the car in its context, in the context from the way the car is charged, if it's an electric car, is operated, is dismissed. So the entire life cycle of the car. That's why we have a system of system topic. And these two main drivers increase the complexity dramatically of the development. By the way, it doesn't apply also to automotive. So my previous company was Airbus. So I've been working in the aerospace domain, and we have the same trends there as well. Okay, so exactly the same trend that applies also to other type of company and other type of systems. But coming back to the automotive, that's our focus for today. This complexity is also a consequence of some trends that are happening that are occurring in the automotive industry. First, the process of electrification. So we have more and more electrified vehicles, and companies are switching more and more to electrify from hybrid. First, there was a big hype on hybrid vehicles. Now we are going to really electrical vehicles, and many companies are switching completely to electrical vehicles. We have next generation of EE architecture, so the architecture get new way of being developed. We'll talk about that in the next slides. And of course, big concept, server zone architecture, okay, where the architecture of the car is completely reinvented, and Enrico will explain this concept better later. And other trends like ADAS, autonomous driving, up to the driver experience, so the infotainment experience. No? The driver is at the center, is not just driving, it's the experience of driving. And of course, all these trends have something in common. They have in common the high presence of software in this mechatronic system. And in the future, 90% of the, let's say, the software will account for 90% of the future innovation that exists in the car. And the basically lines of code in the car will just explode, okay? And this is a good, probably, is a good way, because we are going into software more manageable in theory type of development. However, this creates a parallel and side effect. That's the more software, more codes you have, the more the higher is the chance to come up with software defects, okay? And only in 2018, just one fact, that in the US market, there was basically a recall of vehicle based on software defects that was for a total of 8 million. That was the higher total than the 5 previous year combined. And these trends can continue and continue, okay? So we need to do something for that, okay? Because we cannot stop just this process. We need to be able to manage this process and to drive the innovations within this process. Another example, now I'm going slowly into the depths of the topic, and is that these defects either produce a recall of cars, that's really bad actually, and from an economical perspective, image perspective of the company, but also create a lot of delays in the development. Just some figures here, 40% of the automotive vehicle, 40% of the parts have delays, are produced late, okay? And then let's say that in this context, in this complex context, the automotive industry is going to the next generation E and software architecture, so electrical and software, electronic and software architecture. And of course, we may think, okay, it will be much simpler now because we go away from the mechanical parts and we reduce all the interfaces, all the harness and all the wires, and the architecture will look much cleaner. Yes, of course, but this can also delay more and more the time to market because the team needs to know how to develop this new architecture. It's an innovative new concept, needs to be tested, needs to be developed, okay? So we cannot do it in a traditional way, in the old way, because as I said, we have now this complexity that is rising and rising. And what is this example of simplification that companies are trying to make in this AE architecture? So it's very simple. Today, an average architecture around 100 ECUs, okay? So under small boxes with each box has its own implemented functionality, its own implemented scope. And they communicate between each other with buses and with wires and with sensor and actuators. And all of this is working. Yes. Now, is it efficient? Well, that's why we are probably going into the new future architecture, where there will be a zone architecture, much less wiring, much less ECU, dramatically reduced, and there is a high performance computer, the server zone, that's why it's called like that, the architecture, that will take the power, that will take the lead in having the functionality, enabling, hosting the functionality, and much more products can be developed, much more variants can be developed much faster based on the functionalities that we enable or disable within this big server, big high performance computer that will control the car. Leaders of the automotive industry, and today we have Continental, Enrico represented by Continental, so we have also the witness here from Continental, recognize the importance of doing something to manage this complexity. Here we have just two examples of two big clients of IBM, so Daimler and Continental, and we have the vehicle integrator and the OEM. So, and that also acknowledge the same problem and the same challenge that I've been mentioning so far, okay? So the number of customer functions are exploding, so we need to do something. So their decision was to go with the IBM solution and was to apply, as we will see later, a model-based system engineering together with the engineering collaboration solution, okay? And so I'm trying to introduce now IBM in this context, how IBM can help in this context, okay? And basically, when they talk about using IBM solution, the two leaders of these two automotive companies, clients of IBM, they mainly refer to the engineering lifecycle management solution of IBM. In few words, the engineering lifecycle solution of IBM, it's a solution that enables companies to develop system and software along the entire lifecycle in an efficient way, in a collaborative way, and producing better deliverables for the system and for the softwares. The solution covers the requirements part, so requirement management, the workflow management, that's basically the planning part, the change tracking, and the test management. The test management is all the right side of the V model for those of you familiar with the V model. But also we have one part of the solution that will be the main focus of today. That's the system design, what is called system design. As an MBSE expert, I prefer to call it model-based system engineering because it goes beyond system design, okay? And today we'll talk exactly about model-based system engineering. What is model-based system engineering? Model-based system engineering is a formalized application of modeling to support system engineering. But what is system engineering? System engineering is how I can produce my design artifacts or requirements, design analysis, V&V artifacts like test cases, activities, work plans, from the beginning of the project, how I can produce and manage them from the beginning of the development project up to the end, and also after the project, okay? After the project is in operation. So you can do it in a traditional way. You can do with the support of models, okay? So that's the key role of MBSE. Let's deep dive a bit into this topic. So we learned before about this increasing complexity that is difficult to handle with traditional approaches. Which are the traditional approaches? So first, company use manual documentation, Excel, Word, PowerPoints, just to mention some of them. And we want to go from manual document-based engineering to model-based automated engineering. So we want to take advantage of the models, and the model will bind all the artifacts together, and we can still produce the documentation that we need, but the documentation we produce out of the model, okay? Out of this single source of truth, that's the model. The second topic, many companies still work in engineering silos. So each team does what they have to do, deliver their own deliverables. They don't talk so much. When they talk, they don't understand each other. So we need to go away from this silos culture and go into this collaborative and integrated engineering culture where everybody understands the scope of the work and then has a common guidelines to progress. And there are several checkpoints along the way that ensure that people are doing the right things, okay? That's why we need to overcome this traditional engineering based on documents, based on silos, based on low communication, based on problem during the integration, and go into the model-based system engineering, where the model, the so-called system model, will enable this type of collaboration and will facilitate the work of the various engineers and the production of the engineering artifacts and deliverables. Quick one about what is a system model. So let's start with the system. The system, it's the system that you see in reality, okay? Let's take the car as produced. But of course, the model cannot be exactly like the car as produced. It needs to be simpler and needs to be an abstraction of the system. Otherwise, we will have a duplication of our system in a digital way. That's not what we want, because the model doesn't need to represent all the system, but needs to focus on the high-level part, on the key parts of the system, of the viewpoints of the system that are under the interest of the engineers. And then we distinguish between two types of models. First, we have the descriptive models. So basically model that helps you describing the architecture, the interfaces, and producing the specification. I use mainly for knowledge capture to produce specification, the spec of your system. And then we have the analytical models. The analytical models, as you can see, express a behavior and give you the possibility to verify and test this behavior, okay? And to check if the behavior is as intended, as designed. This is the main difference, okay? So today we will show you a model, descriptive model, and then we'll go into the analytical model. That's what Enrico will show you later. But which are the key things? When a company starts MBSE, which are the three pillars of MBSE, okay? So first of all, process and method. So we need to start with the process and method. So how do we perform system engineering? How do perform the company processes that we have in place or that we want to put in place in a better way, using system engineering, using models, using a language and a tool, for example. Then we need the language, of course, I mentioned already. So we need to keep a notation and a semantic that people can use to understand each other. For example, the system model is represented in system modeling language. And then we need to take the tools, okay? The tools that are needed to implement the methodology, to implement the processes, they use a specific language, SysML language, and they can be used by the users, okay? So the tools help implementing, actually a key factor in the implementation of model-based system engineering. Talking about tools, we have Rhapsody. And Rhapsody, it's basically the oldest tool and still a market leader. It's one of the first tools of based on a UML and then on SysML. And it's, let's say, as an MBSE expert, I feel like really proud to work with this tool because it's like the pioneer of software engineering, of system engineering. And Rhapsody supports all these things that I mentioned before. Enrico will go into this in a few seconds. So the design of the architecture, it means descriptive model with UML or SysML, specify the interface, describe the interface, not just interface control document with Word and so on, but we can really model the interface there of our system, of our softwares. Linking the model with the other artifacts that are not models, like requirement, test cases, work items. Executing the model, executing this analytical model, so we can test them, see they are really doing the behavior as intended, okay? Run the simulation. We can use model to run simulation within Rhapsody with other tools that interface with Rhapsody, and also for those that are into the software development, generate code. These are just some of the features that Rhapsody has in support of MBSE, and Enrico now will deep dive with example into some of them. Thank you, Enrico.
Good. Okay, then I will take over. Okay, some brief words. MBSE at Continental. So some brief words about Continental. Continental is, beside maybe some of you guys know this, famous for tire business. But beside of tire business and the rubber business, which is called ContiTech, automotive is by far now, or became by far, the biggest group within the Continental Corporation. And I'm working for the architecture and networking group, which is a kind of a specific group for all the other four business areas: safety and motion, autonomous mobility, user experience, and smart mobility. So what architecture and networking is doing? Architecture and networking is basically building the platform for all the other business areas. It builds the communication backbone by systems. We call it also an enabling system. Those other functionalities for autonomous mobility, for the user experience, can run on this network, can run on computer platforms, on processing platforms to execute their functionality. So as architecture and networking, we provide several products. We call them, as Marco already said, high performance computers as the central processing units. Those units, they don't have a lot of interfaces besides communication, but they have 10 to 50 times more power than classic embedded electronic control units to enable the future calculation of complex functionalities. We are also, beside in telematics, active to link the car to the rest of the ecosystem. We call it also the ecosystem architecture, what we derive out of this ecosystem, like V2X communication, vehicle-to-vehicle communication, as you see here also illustrated. Being recorded. We provide classic solutions for smart access using dedicated keys, but also including connection to the cloud, that you can open your car with a smartphone very easily, that you can access with your smartphone the car to illustrate, to show vehicle status information, and so on. And of course, classic business, body and actuator controls like lift gates, door control units, central body computer for the typical interaction with the user, activating lights, and so on. And Continental is also leading in advanced antenna solutions to connect our vehicle to the rest of the ecosystem. Let's now catch up what Marco said before, that we have in the recent years a revolutionary change within the automotive. We talk about that the cars are changing from a component-defined architecture to a function-defined architecture. What does it mean? A component-defined architecture is fixed during design time. So whenever I want to place a functionality in a car, hundreds of engineers are sitting together and designing for this and that component what the car functionality should do. And then it will be developed, designed, realized, produced, and the car has then a fixed functionality, which is hard to update for future functionality without a bigger architecture change or a lot of software change within those software components. Each of those ECU have then basically domain separated and isolated functionality, which also results in lots of wires, a heavy wire harness. And together now with the change to the electromobility, it gets really the need to lighten up the vehicle, since the battery is also a heavy component. So reducing the wire harness, reducing the numbers of wire, is to bring more and more communication lines between those units and to reduce the number of units. In the past, we had the focus of pleasure, safety, and comfort as a user expectation. While now, the user expectation is becoming more and more that the car is like a smartphone on wheels or a smart IoT device on wheels, where the user want to have more and more functionality over the lifetime of the vehicle without even going to the service station. And this can be achieved by having new high-performance computers as central computing units within this vehicle, paired with zonal controllers, which are responsible for a certain rear or front zone of a vehicle to sense and activate certain hardware functionality where a user is interacting with or where the environment is influencing the vehicle or where the vehicle is influencing the environment, for example, with lights, with acoustic signals, and so on. And a big difference also between the classic car design and the function-defined architectures that those new cars are permanently connected to the cloud, collecting data from backend systems, giving remote access, make fleet management possible, and so on. The car, you can say, like any other smart device, is always connected. This comes together with an increasing complexity of functionality. You can imagine when you want to place a functionality in a high-performance computer with no hardware interfaces, basically beside the communication interfaces, you need to cut your functionality into such pieces that you have a sensing part, an actuation part, and a kind of a controlling part where you focus on the user perceivability of a functionality. And this needs a high skill set for the system engineers how to do that. And how do we come to this is to develop, beside the language, what Markus said, beside the method, also an additional system engineering way how to design such kind of systems, and we call it the server zone concept, which gives us the highest flexibility. Let's have a little bit a deeper dive into that. This is a kind of a typical example to show, to illustrate the architecture. The system is basically designed out of one or more high-performance computers, which have mostly only power supply and some communication lines connected with an Ethernet backbone to talk to each other and to talk to so-called zone controllers or ZCU, zone control units, which are responsible for a certain area within the vehicle to sense, to actuate, to control in real time specific needs. For example, the important thing is now, in the past, the car was divided also by the organizational unit into certain domains like a chassis domain, power domain, body domain, and so on. With this new zone controller concept or server zone concept, we overcome these domains, and it gets possible by those backbones of zone controllers and high-performance computers to put cross-domain functionality or to deploy cross-domain functionality into those controllers and computers. So it can happen that you have a rear zone where then some rear lights control together with some ADAS functionality to sense with some radar or LiDAR devices, some picture imaging, which is then pre-processed and then later hand over to the ADAS functionality processed in the high-performance computers. So in our understanding, only with this flexible architecture, we are able to cope the complexity in the future. And a big help to create a consistent architecture is model-based system engineering. When we have now a central body controller with maybe 8,000 requirements and I don't know, 12,000 test cases, we will end up with a high performance computer, maybe with 20 to 30,000 requirements in this classic way written, which nobody can handle anymore. And therefore it's getting important with the new architecture also to change the way of developing it, to focus more on the design using models, using functional description in a semi-formal manner instead of textual description with requirements. And this is what we try also to achieve with our approach by developing a framework within the company, supporting and guiding the system engineers to make the right decomposition, the right clustering of the vehicle, and to cope complexity. One important factor on this is the time to market. So this complexity you cannot handle by individual and development of those computers or zone controllers for each and every customer, for each and every car manufacturer. So we built backbone architectures which we can reuse. We call it zone controller platforms, high performance computer platforms. And with model-based system engineering, we are able to reuse a lot of artifacts what we have produced within those units as a system, so that we can reduce the development cost and be much faster in the future with our design. Also, with model-based system engineering, since we change from an informal requirement description into a semi-formal or even formal description, we can develop consistently systems until ASIL D, the automotive safety integrity level for the people who might not know that. And we can automatically fulfill by principles of the systematic engineering the quality aspects like ASPICE. How do we come now to that? And I want to show this later then also in some live examples in Rhapsody. We are using also then a set of tools from IBM like Rhapsody, like the config management, the global configuration, like doors for requirements still, but we use them in the future doors next generation and so on. And in this combination of those tools, we are able to build a transition from the classic document-oriented design, which is still a big portion, into the model-based design approach. This cannot be done just with a big bang. Today we do requirements and doors, and tomorrow we do everything in Rhapsody. This will not happen. This will be a gradually approach. And I'm going to show now how we can do that by some simple steps. So we are coming now to a case study where I try to explain this with some simple functionality of a light function. Otherwise, you get overwhelmed by the complexity, what is behind such kind of server zone concept. Let's focus on 7 main steps, what we need to do together with an architecture framework behind to develop such kind of systems. At first, what we need to understand from our stakeholder, which is, for example, a car manufacturer, is what kind of features they want to implement. Therefore, we can make a so-called feature definition where we use a kind of a variability management viewpoint. So we are using not just SysML, we are extending the SysML with different viewpoints and abstraction levels to get the scope and the concern correctly understood by each and every system engineer. So after the feature definition, we need to do a system context. We need to understand how our system of interest, for example, here in this example, a vehicle, is being interacting with the ecosystem, with the environment. This comprises the composition of actors and the system of interest into a block definition diagram. We build then the interaction. I will later show this, how it looks like in the model of those parts and see in what way they are interacting. And further, once we have then our system context defined, we know how a system from the analysis point of view should look like. Therefore, the so-called operational viewpoint, which is the analysis view for a system engineer, we then refine with a so-called operational analysis on that same viewpoint using use cases and activity refinements to further break down our functionality, what we intend to develop. This breakdown is done in a recursive way until we reach a point where we say, on a certain level, like on a vehicle system level or on a system product level, we want to design a certain functionality. So we jump into a functional viewpoint. And in this viewpoint, we make then our breakdown, embed the identified functionalities or the activities, what we developed into those functional elements, and design of those functional elements a bigger network of functionality. And this, of course, need then to be verified. So in step 6, beside step 5, which are interchangeable, we need to verify this. And this is much better to do with a model, even with an executable model, than with a textual description. A further step is then also to build the logical architecture. Here we use a so-called logical viewpoint. But what does it mean? We take our functionality, our function blocks from the functional viewpoint, and deploy them to the nodes, what you have seen in the previous picture, to see in which zone of a vehicle, what kind of functionality we want to place. We link then those functionalities into the nodes, and then let them communicate and see how performance aspects can be considered, what kind of bandwidth of networks we need, like do we need an Ethernet, do we need a CAN, do we need just simply a LIN bus, and so on. And finally, the traceability. So, okay, let's have now a look how those 7 steps are applied. And here I jump now into Rhapsody. Architecture is in the end also here the communication with your stakeholders, the communication with your developers, what you want to have, what you want to achieve, what you want to develop. So a panel diagram, as Rhapsody supported, is a very nice way, after you have your function designed, to communicate this function, to verify it. And I want to show you in a little bit a demonstration how this can be done. So when you have a model which is executable, I just come back to the way how we get to this, but I want to show you in a kind of a preview how this should look like. We can play with several switches with buttons to simulate a certain functionality. Let's assume we have here a light function. The light function can be manually treated, or we let the vehicle do the job and say, manually, we switch on a light switch, which is then represented by a hardware switch. We can really develop deeply hardware interfaces for a sensing to control the functionality, and then switch on the light. Or we say we let the job do by the car, and then, for example, the light intensity, what we measure as an impact, as an effect from outside, will be used to control the lights. For example, when the light is changing below a certain intensity, then after a certain time, which is of course being evaluated by empiric determination, how long it should take when I enter a tunnel or when I run through a shady area in the street and so on, to activate then here, for example, the lights. I can simulate also dynamic behavior like blinking. I can simulate a prioritization between blinking and a hazard, how this behavior then optically should look like. And finally, when I want to verify, and I have developed, for example, a state diagram, I can even illustrate this to support my verification so that I don't have to build in all my brain the functionality, which is often the case when I use a classic development, when I read requirements. I basically have to build up the functionality in my head when I combine requirements. And here, model-based system engineering helps dramatically to visualize your intended behavior you want to achieve. And for example, when we go to Xstreer Light, to the static light control, then you see when you model it right, that you can have a kind of a state diagram verifying then your intended behavior. For example, I have here a light switch from the panel. When I change this light switch, I can also place the same light switch on my diagram. It's reflected automatically. And I can change then here an operation state. I can switch the light off. It's returning back, for example, to the auto light. I can completely switch off and manually say, I don't want to have any auto light control, and so on. When I go to the off light, when I switch the switch off and I go to an auto position, which can be reflected by graphical elements, what kind of signal, what kind of status I have. Then, for example, when I change here the light intensity, I can then switch between those states and I can verify that. You see here a way to design your system, to design your functionality, and even to verify it. What you have seen in previous slides, you can also make an verification using sequence diagrams for a specific sequence, what you want to show, how access need to be done, in what kind of way. You can simulate security and safety behavior. You can place dedicated safe states to fulfill the ISO 26262 requirements, and so on. So with a semi-formal approach, as you see here, we can much better cope the complexity of a system. Let's have a look to the verification. The verification, let's have a look to the traceability, which was one of the last points. Traceability can be very nicely shown in our design tool, even as well, beside in DOORS, that, for example, we have functional or technical features which are then being derived with a trace link to a requirement. The requirement is being satisfied by a certain system element, and so on and so forth. So we can even import requirements, make them graphically visible. We can say how we refine an use case here, in our case, for example, a system use case or a continuous use case from those requirements. So the architecture is building basically the center of the product description, which makes us able to cope complexity. Let's come back to the presentation and have some few numbers at the end. When we compare modeling and classic system, when we compare the modeling effort with the normal system engineering effort, we have here a ratio from 30 to 70%. So 30% is the pure modeling in a tool. So people don't need to be scared. Modeling are so much effort. No, 70% is thinking what you want to do still. This no one can take away from an engineering job. And 30% is pure modeling. The other one is requirement writing effort. When you compare classic requirements, as I said before, and you model the same thing, with one picture, you can say more than dozens of requirements. So I see here also a ratio between 1 to 3 means the effort is 3 times higher in writing requirements from the amount of time. A big portion and a big benefit is the object-oriented approach of a model-based system engineering compared to a document-based principle. Here we can reuse up to 80% of already developed artifacts, from requirements down to the functional design and the deployment. A time to market ratio, I see here also in a very good scale. Once you use model-based system engineering in a platform environment or in a function development scenario where you want to reuse functionalities, you can really support individual projects with a ratio by 5 to 1 by 5 times faster once you are able to reuse those elements. When we look to the quality factor, executable MBSE is produce much higher quality compared to, for example, a documentation like Microsoft Visio. Here I see a factor of 10 to 1. But there's a thing what we need to consider. This is the time to the organization rollout. So MBSE is not a big bang, as I said. So we need, in our experience, 5 years and more gradually to change from a classic design, from a classic system engineering principle to a complex design using MBSE. There's a lot of education and training necessary, because without that training and without the understanding of the language, of the methods, and of the tools behind, it's very difficult to reach this. And those challenges are the next scope, what we have to overcome, so that we can develop our units in a high reusable manner. So thank you for listening, and I think we can go back to Q&A session.
Thank you, Enrico. Thank you very much. It was really interesting. And of course, this session will be also recorded, okay? So it means that you can later on, maybe Preti can mention that later, explain how to do it, but you can also access the recording in a later stage. So do we have any question, Preti, from the audience?
Yes, Marco, we have two questions.
Okay.
And again, for the participants, if you have any questions, please post it in the chat on the right-hand side. Marco, the first question is, how do I know when my company is ready to start MBSE?
Okay. Yeah. Well, I don't know, Enrico. I can give my point of view, and then maybe you want.
I can add on some comments.
You can add on. Okay, very quickly. I've been doing this in the last 10 years as a consultant, as leading transformation also in company like Bombardier, Airbus, just to make a couple of names. And first of all, you need to understand if the company have in place a system engineering, because everything starts with system engineering. If you don't have system engineering, if you don't have good system engineering, good requirement management, VMV processes for verification validation, you can add the models on top, but they are not going to help, okay? So the idea is really start with system engineering and then usually see if the company has a potential, has a certain maturity in system engineering, then we can try to adopt MBSE. But first of all, I would say the most important thing is the company mature in system engineering. So they have formalized processes. And of course, everybody can start with a POC, proof of concept, but then to really adopt it on large scale in a company, then we need a certain maturity on system engineering first. I'll give you a short example. Some of the clients in Asia Pacific wants to start with MBSE. Then I visit them, and then I see that probably for them it would be better to start first with requirement management, with those next generation, our requirement management tools, and to have a good requirement management processes, test management processes, and then later, step by step, introducing the models. That could be probably a good way. I don't know, Enrico, if you want to add something.
What I can add is you need your people beside the mindset that you want to go in this direction, ready to understand the fundamentals. So if you don't educate and train people in understanding the language, UML and SysML, you don't need to start because they cannot read and understand the diagrams. So when you have done your architecture using Visio and free floating graphics arrows, which are unknown to others, this is the first sign that people cannot communicate properly. And you have to harmonize the understanding and to introduce the language. Once you have the language, as a next step, you need a method, as you say, that behind, and an adaptation, because SysML is just a language to describe with a semantic behind what you need to do, but you need to adapt domain specific for an automotive domain or for an avionic domain or whatever you have on domain, train systems and so on. You need to understand what do you want to develop, what are your constraints like platform development, individual projects. And once you understood this, you need to adapt and shrink these big language capabilities to what you want to achieve, what you want to communicate with your architecture. The best way is then also to start simple without full model-based system engineering in execution. So Marco said you need to have a system engineering process at all ready. This is a precondition to start any of those modeling. When you see the need that there is a platform development necessary, that you want to reuse elements, when you struggle with reusing your classic artifacts and documents, when you have a lot of effort to reproduce context for different projects, then you're in a phase where you say you should think about how I can improve my reuse by making a system engineering approach, producing reusable artifacts, starting, for example, from a function development, single artifacts to embed into systems, what you just develop once, and then you have it, and then use it again and again and again.
Thanks, Enrico. I think it's clear because I think it was we can talk for hours
Yes,
about that,
for sure.
as you know. So I want to move to the next question. We can try to answer most of them, if not all of them, because I see now are coming more questions. So maybe next question that we have. So what is the strength of Rhapsody in adopting MBSE? Enrico, I let you answer this question because
Yes.
I'm the tool vendor, so I want the customer answering the question.
Yeah, in our company, we had long years fights which tool to use. And finally, it has been decided to go to Rhapsody. Why? We had also other tools like Capella using the Arcadian method, which was also a method behind. But the problem was a proprietary language. So if you want to communicate to our stakeholder, to our customer, to our clients, to our developers, we need to talk the same language. And SysML is a language base. So we have chosen a tool which is UML and SysML capable. Why to choose also further Rhapsody was we evaluate other tools, is the consistency, how the model is being constructed, and the philosophy, how this is being shown inside the tool. This is in that tool, even if it's an old tool, but it's very mature in this regard. And it shows in an easy, understandable way how elements are linked each other. And you have a very consistent way to define interfaces. You can, with less effort, change from drawing into modeling, as long as you understand the fundamentals of a language.
Yeah, and also, by the way, thanks a lot, Enrico. And just to add on that, in January, in Q1, we will have a new release of Rhapsody. So next year will happen a new modernization. This is now old software, so you're right, very mature. So we invested a lot in modernizing it. Okay, just to add on top. Thanks, Enrico. I see other questions here. It's a long question from Peter. So nice to see you, Peter. How we can increase the acceptance of MBSE for electrical engineers and mechanical engineers. SysML and therefore Rhapsody is very software driven. Electrical and mechanical engineers have issue with starting MBSE. Otherwise, MBSE for software exclusive is a waste of time. Interest in your opinion? Wanna start? Should I start, Enrico? How do you want?
I can maybe answer things.
Please, go on.
We have developed an architecture framework within the company, especially with a target to be have a seamless approach between system, software, and hardware. So, and Rhapsody is perfect doing this by profiling the language with certain extensions. Especially for hardware, people are scared at the beginning, but I can tell you the object orientation of the language, of the philosophy, is perfectly helping to define your physical or technical components, to define a technical interface, to embed them into bigger systems, and to let them even play if you want. Object orientation is the best approach for a future system, and especially also for hardware block diagrams. Besides of software, you can model everything without really having the need of this software philosophy behind. It's perfectly for hardware development and hardware architecture.
And maybe to add on that, because Peter probably is interested on how to start it out, how to convince people, I can tell you what Enrico says is very important: profiling, simplifying. Okay, you simplify the diagram that they need to use. Probably some mechanical engineer, it will focus mainly on IBD and BDD diagrams for SysML. So you have tables, you create tables because engineers understand very good tables out of the models. So you use tables and models. So you find a way to simplify the acceptance of that, okay? So the tool is fully flexible, and that's why I recommend customization, simplification and customization to let them start. Focus on what they need, structural diagram, for example, first. I see another question, and customer requirement from Narayan. I don't know if I pronounce correctly. Sorry for that. Customer requirement change time to time. How model-based approach is flexible to absorb it? I will answer quickly, if I can, Enrico. So
Yes.
you never have only models. You have requirements and model. For example, if you go with IBM solutions, you have your requirement database where you have your requirements, and you have the requirement links to the model object. Each and every time you change your requirements, you will have a flag that will tell you to update the model. So it's really important that you keep consistent your model and the requirement. Now, if you have, imagine you have your requirement database, and you import the requirement into the model, you start modeling with the requirement in the modeling silos in your MBSE tool that is not integrated with the requirement management tool, then you cannot keep the consistency. That's why it's fundamentally important that the requirement management tool, it's linked and continuously linked through OSLC, as we do, for example, with the models, in order to keep the consistency and deal with this continuous change that will happen along the entire life cycle. I don't know if I answered the question. I hope so. We have 3 more questions. Maybe let's try quickly. This is from Shiva. How do we address the scalability in terms of MBSE referring to multiple CAN networks in ECU by shifting to functionality version? As most organizations end up shifting to software design perspective than system approach. Did you get the, Enrico? I get the question is for you, Enrico.
Oh, I hope. Yes, of course.
In few words, maybe, because I would like to try. Yes.
You can model complete communication stacks within the system model. You can also define detailed protocols. You can define signal message collections. So in my opinion, and as we are using it in our automotive, we are using templates for creating signals, messages, and so on to create also for multiple networks, even gateway solutions. So it is possible, but it's a bit more tricky to answer this long question in all details. It is possible. And
by the way, I think they can send you also the question per email, right, Enrico?
Yes, I can answer for sure. Any question you have, you can contact me and I can try to give a comprehensive answer.
Yeah, I will go quickly in the 2 minutes. How does global configuration contribute in MBSE from reuse perspective? Well, if I talk about my history, I first was an expert of product line engineering, and then I moved into MBSE. For me, the two topics goes together. If you don't have a good configuration management approach, not just of the models, but all the artifacts that you have to deal with, and that's why come global configuration management, it's very difficult to implement MBSE. I see many companies, big companies, starting MBSE, but then they're not able to configure, to version the models. And that's a very big limit of MBSE. So you need to be sure, and that's one also the reason I joined IBM, because I think they have the overall solution for it, that you have a configuration management versioning system in place, not just for the MBSE model, but also of the artifacts that interface that are linked to the MBSE models. So that's a quick one, but if you have more questions, please let me know. So I will skip the doors question because it's not relevant for this webinar. Does SysML integrate with Modelica system simulation tools for behavior modeling? Of course it does. And there is also a standard called SysFIS that was developed in 2018. You may have a look at that describe the integration between SysML and Modelica language, and also SysML and MATLAB Simulink. So you can use FMU approach, importing Modelica model into SysML, and the other way around, exporting SysML model, SysML structure into Modelica tool. Yet SysFIS is the name of the standard. You can have a look at that.
You can also integrate MATLAB into Rhapsody.
Yes, of course. Yeah, I mean SysML.
And the other way around.
Correct, Enrico. A model from Nico, Anna, and Nicolas from Australia. A model is the most useful when shared and understood by all stakeholders. Rhapsody interface not always easy to navigate. I agree. How did you overcome this to get system engineering to use it? So as Enrico said before, we need to simplify the tool. So we need to reduce the views. We need to limit the multiple things they can do in Rhapsody. We need to improve the usability of Rhapsody. So there is something we can do by ourselves, like profiling, customization, simplifying the diagram, simplify the elements, the helpers in Rhapsody. So this is something we can do. And then, of course, our development team is working, as I mentioned before, beginning of next year. They will develop a new UX that is to improve the usability of the tool. So it will look much easier to use. The visualization will be much better. It's a combination of both. One is on our team that is working on that. One is on the MBSE expert that are helping companies in simplifying. So I'm working for Airbus, and we spend a lot of effort in simplification of the framework that there was called MOFLT, mission, operation, functional, logic, and technical, so covering all the levels. We spend a huge amount of time in customization, simplification, okay? But once it's done, and of course we can help with that, then customers will accept much easier, in an easier way, the solution. I think we need to close because we are already over time. Maybe I skip some of the questions. Sorry for that, but please feel free to contact me also for questions.
Yeah, I think you took all the questions, Marco. So thank you, Marco. Thank you, Enrico. This was a very interesting session. The number of questions that we got was a reflection of that. For everybody's reference, we'll be sending across the recording of this webinar for your future reference. And we'll also send you the contact details of our eminent speakers today. So if you have any questions, do reach out to us. Thank you and have a nice day, everyone.
Thank you.
Okay, thank you and have a good day. Bye-bye.
Bye-bye.